It's not a surprise that it's about dense retrieval, but I think it's a surprise that it's not about LLM. So, okay. So, hi everyone. I'm Tamer from Qatar University. I'm pleased to present today the work of my students, Salam and Sohaila, who couldn't come and attend the conference. The paper is titled "Graded Relevance Scoring of Written Essays with Dense Retrieval." So the problem that we are talking about here, or we are working about here, is automated essay scoring. And this is a new problem or a new domain in which dense retrieval was never applied. What is automated essay scoring? Well, in standard exams like TOEFL, GRE, or ACT, the student get a writing task, and he or she is supposed to write an essay in response to this task. Now, instead of giving all of these essays of all students to humans to grade, we would like to build a system that can automatically grade those essays. So that system can provide one overall score. We call it a holistic score. And in this case, this is called holistic scoring. This is just giving one score overall that will summarize the quality of the essay. But that's not very useful to students. It's more useful to give students individual scores on different dimensions of the quality of the writing, like organization, relevance, coherence, development, structure, style, and so on. So this is called trait scoring. If the system is able to provide those individual scores, this is trait scoring, and each score is called a trait, or each dimension is called a trait. And in this course of work, of course, we are focusing on relevance, the relevance dimension of the essay. So here we mean the relevance of the essay with respect to the writing task prompt. And the word prompt here has nothing to do with LLMs. It's the prompt that the student get to describe the topic that the essay should be on. There are two ways to learn an automated essay scoring, or in short, AES model, for a given writing task. The first one assumes that we already have graded or labeled some essays on the same topic or the same task. And then we will be, the system, the model that will be learned will be tested on the same task, but of course on unseen essays. So that's called task-specific AES, which is not very practical because we have to really label or grade some essays for a new task. The other model, which I think is more practical, or other scenario, in that scenario, we have multiple tasks that are previously given to in previous exams. So we have already graded essays for these tasks, but and this will be available for training, but for testing, the system will be tested on completely unseen tasks, with, of course, unseen essays. This is called cross-task AES, or also known as cross-prompt in the literature. How did we tackle this problem? We approached the problem using dense retrieval. We get, of course, dense representation using a dense encoder. The dense encoder takes text and provides an embedding vector that will represent the semantic features of the text. So in IR in general, we have a query, we have a document, we represent each of them, and then we can compute the similarity between them by computing the similarity between the embedding vectors. For dense retrieval, we have a query, we encode the query, we encode also all the documents that we have, and then being encoded as dense vectors, we can view them in the semantic space like that, and then we retrieve documents for the query within the neighborhood of the query in the semantic space or in the embedding space. Now, how can we apply that for AES or for automated essay scoring? Well, we have at least two alternatives. The first one, we can view the task prompt that's given to the student as the query, and all the essays that were written for that task as the documents. The problem here is that the prompt usually is very short, and the essays are mostly much longer, so there will be incompatibility in length, and that might not be very effective. The other way is to use, is to ignore for a bit the task prompt and use the test essay as the query, and labeled training essays, labeled essays or graded essays as the documents. And in that case, the length of the query and the documents will be comparable, so the similarity will be better estimated. So as a view of that idea, in the semantic space, we will represent all the training documents, and in our case, this will be the graded essays that already manually graded. And then when we have a new test essay that is not graded yet, we represent it, of course, in the same space, and then we find in the neighborhood whether we have relevant essays to the topic or not. This is in case that we have binary relevance. But in AES, usually relevance is graded by a score, sometimes from 0 to 4, sometimes from 0 to 5, even more. So it's not binary. Relevance here is not binary. So we have to adapt dense retrieval for graded relevance. In graded relevance, the document can be assigned one level out of many levels, from 0 to n. It's not just 0 or 1. How can we do that? Well, building on the same idea, we represent all the labeled essays in the semantic space. Now they are of different colors because they are different relevance levels. Some of them are at level 0, some at level 1 and 2 and 3 and so on. Then we represent the test document, which is in our domain, or in our case, the essay that we want to grade. And again, we look at the neighborhood. Now, when we look at the neighborhood, because we have so many relevance levels, we might not have a good prediction. Because individual essays will represent the relevance levels, and that might not be really effective. So we proposed another simpler idea, which is to compute the centroids of each, the centroid of each relevance level, and that centroid will represent that relevance level. And instead of computing the similarity between the new essay or the new test document with the neighborhood, with the documents in the neighborhood, we compute the similarity between that document and the centroids of the relevance levels. And then, of course, we assign the score to that document with the score with of the closest centroid. So it's basically one nearest neighbor with centroids. It's very simple. So giving you the whole picture in AES again, so we have the training essays. These are already manually labeled. We assume that. We encode them. And by encoding, we assume that the encoder will be good enough so that it will cluster the documents based on their relevance level. And we compute the centroids, and then we compute the similarity with the test score, with the test essay. Now, in the other scenario, when we don't have any labeled data for, or any graded essays for the new task, we only have from previous old tasks, we still can apply the same idea. We have, but with a simple extension that I will mention in a second. But now we have training data from other tasks with different tasks. So when we encode them, one thing that can happen here, or expected, is that the encoder, because these essays come from different tasks and different topics, they might be clustered based on the topics instead of the relevance levels. So computing the centroid in this case will not be efficient, or will not be effective. And that's basically because the dense representation is usually topic dependent. So when we have essays on different topics, they will be separated in the space based on the topics rather than based on their relevance levels. So The solution here is that we need a way to convert to a topic-independent representation. We need to disentangle the essay or the essay quality, the quality of the writing or the relevance level from the task or the topic. The idea, again, is very simple. We just, the idea that we proposed is to just remove the topic from the essay representation by subtracting the embedding vector of the prompt or the topic from the embedding vector of the essay. Now it will just kind of removing the semantics of the topic from the specific semantics of the topic from the essay. If we do that, then the clusters will come back to be relevance dependent, and we hope that by computing the centroids, now the centroids will be separate, and thus we can now assign a score to any unseen essay, even with a new task. So that's overall the idea, encoding, and then doing this, the extension by removing the topic vector, and then doing the one nearest neighbor. Still, there is a problem, which is that the new tested essays should be scored based on their own task or their own topic. So we still have to incorporate somehow the similarity with the target task prompt. So what we did is that we computed the similarity, scaled it to the scale of the relevance levels, and then we assign the score of the average of the semantic score and the similarity score and the score that we got from the centroids. In our system or in our work, we used Retrieval, dense retrieval model for many reasons. It's trained with contrastive learning, which is a good fit for our problem, less biased towards topics, and it has strong performance in other tasks. We also did fine-tuning. Since this is a new domain, it's a specific problem domain, so we further fine-tuned the Retrieval using contrastive learning. For time, I will just ignore these. So for the experiments, we used the ASAP or ASAP++ dataset, which has 4 topics and about 1,700 or 1,800 essays for each topic. We used quadratic weighted kappa as an evaluation measure, which is a correlation measure between 2 ratings. The 2 ratings here are the system and the human. And we compared, of course, with the state-of-the-art baselines. For the task-specific ES, when we have already graded some example essays graded for the task, here is the results out of the box with the Retrieval. So this is without any fine-tuning. We used Retrieval just with one nearest neighbor with the centroids to assign scores. And as you see here, we didn't beat or we didn't outperform the state-of-the-art, but it was really a substantial correlation. And that's without any fine-tuning. With fine-tuning, the performance was much better than the pre-trained model, and it established a new state-of-the-art performance compared to the state-of-the-art that is listed in the table here. This is a visualization. I think I have to skip it. With the task-specific scenario, we have to manually grade many essays, which is, I think, not practical. So we tried also to see the effect of having few shots. Instead of training on all labeled essays, we try to train on few shots, and the message here is that with 30 shots per level, which is about 150 labels, we reduced the cost of the labeling or the grading to 85%, and sacrificing 10% only of the performance. Finally, in the cross-task scenario, we achieve a very bad performance without the trick of the disentanglement. the extension, the simple extension that we did. With the extension, we approached the performance of the state-of-the-art a little bit, and with the similarity with the target task prompt, we are on bar. We had a performance that is on bar with the state-of-the-art. The key takeaway messages here are 5. First, we applied dense retrieval in a new problem, which is automated essay scoring. We proposed a novel and simple approach for graded relevance that can be applied to general graded relevance tasks. With fine-tuning, we established a new state-of-the-art performance for the task-specific scenario. With few shots, we reduced or we can control the cost effectiveness trade-off. We managed to reduce the labeling cost by over 85% while sacrificing 10% only of the effectiveness. And finally, we proposed a simple adjustment to work for the cross-task scenario. And that adjustment achieved a performance that is on bar with the state-of-the-art. Thank you.